Morning, everyone, once again, and welcome to session number 2. So please make sure you're in the right session. And the topic for this session will be on research on energy and industrial development. And please let me introduce you to Associate Professor Dr. Pitsanupong Kanjanapayon from Department of Geology, Faculty of Science, the chairperson for today, and Assistant Professor Dr. Nampon Insin, Department of Chemistry, Faculty of Science, who will be the co-chairperson today.
Good morning, everybody. First, we will start for the session number 2, and we have 15 minutes for each speaker. First, I would like to welcome Associate Professor Dr. Napida Hinchiranan from Department of Chemical Technology, Faculty of Science, to present about her research about removal of polycyclic aromatic hydrocarbons in waste-type pyrolysis or via catalytic hydrogenation. Please, Professor Napida.
In the title of removal of polycyclic aromatic hydrocarbons in waste-type pyrolysis oil via catalytic hydrogenation. Waste-type is non-biodegradable and it requires hundreds of years to decompose in the landfills. And although we have like a recycle process, but it's not enough to remove all of the waste-type generated in the world. So we have like a pyrolysis process to convert the waste-type to the alternative energy. And because of the high efficiency of the pyrolysis process, so we can get a lot of the liquid yield, and we can apply it as the waste-type pyrolysis oil to the combustion engine, and we can call that the WTPO. Actually, in the waste-type pyrolysis oil, we cannot apply directly into the combustion engine because it has like some toxic compounds. Such as the sulfurous compounds derived from the vulcanizing agent and the polycyclic aromatic hydrocarbon derived from the Diel-Alder reaction during the pyrolysis process. Actually, for the sulfurous compound, we have the hydrodesulfurization process to decrease the amount of the sulfur in the WTPO. But for the polycyclic aromatic hydrocarbon or PAH, there has not been reported yet to decrease the amount of it in the WTPO. So in this research, we focus on the PAH inside the WTPO. And normally, the polycyclic aromatic hydrocarbon is the name of some of the chemicals that has the aromatic ring, about the 2 to 4 rings. And normally, the PAH has some harmful for the human and the animal health because it can provide the carcinogen and the cardiovascular disease. And it also contaminates in the environment, in the soil or in the wastewater. And it also like a source of the PM 2.5 generation, and it can induce the air pollution. Actually, in Thailand, we have like a regulation to limit the amount of the pH in the diesel. It's not over than the 11%. But we have the report that some small amount of the pH can harmful for the organism in the body of the animals and the human. We have like a process to eliminate the PAH such as the thermal treatment, photo degradation, cracking, or the chemical oxidation. But this process shows the slow decomposition rate with the high energy consumption. But for the chemical oxidation, it can provide the intermediate with the higher toxicity, and it can be dissolved in the water resource. So the hydrogenation is the suitable method to convert the pH into the less toxic compounds. And this process requires to use the metal catalyst. For the normal metal catalyst, actually it has the high activity for the aromatic hydrogenation, and it also has the high resistance to sulfur or the nitrogen poisoning. But it's expensive and it's limited to apply in the large scale application. So we need to use to seek for the non-noble metal catalyst like the nickel, because it has also get the high activity for aromatic hydrogenation and it's not expensive. But the disadvantage of the nickel catalyst is to the sulfur tolerance is very low. So we need to get like the suitable promoter to enhance the efficiency of the nickel catalyst. And in this research, we select to use the molybdenum, tungsten, and the platinum as a promoter for the nickel catalyst because the waste type pyrolysis oil, it contains a large amount of the sulfur compounds. So the objective of this research is to comparatively study the effect of the nickel molybdenum, nickel tungsten, and nickel platinum supported on the gamma alumina catalyst to remove the pH in the WTPO. And we also investigate the effect of the reaction temperature and initial hydrogen pressure on the degree of the pH removal from WTPO. In the experiment, we divided as two parts. The first part is about the identification of the pH compounds in the WTPO by using the GCMS and the fractionation by using column chromatography. And then when we know about the main compounds inside the WTPO, we use it as the model compound and hydrogenate it to investigate the suitable catalyst before we add it into the hydrogenation of the WTPO. And then this slide shows the textural properties of the top of the catalyst and the nickel oxide crystalline size. And you can see that before we add the promoter into the catalyst, it shows the surface area about 157 square meters per gram. And after we add the molybdenum or the tungsten into the nickel catalyst, the surface area tends to be decreased. But it's not for the nickel platinum. It still shows the high surface area about 170 square meters per gram. And to see the effect of the promoters on the nickel oxide crystalline size, we use the XRD and Schiller equation. And you can see that before adding the promoters, the nickel oxide crystalline size is about 27 nanometers. But after we add the molybdenum or the tungsten, the nickel oxide crystalline size decreased to 70 nanometers, especially for the use of the platinum promoter. The nickel oxide crystalline size decreased to the 9.6 nanometers. It indicates that the addition of the promoters can enhance the dispersity of the nickel oxide throughout the surface of the gamma alumina. And because the catalyst that is suitable for the hydrogenation is the acidic catalyst, and this table shows the acidity of the studied catalyst, and it shows that they apply the molybdenum promoters into the nickel catalyst, it shows the higher acidity because of the molybdenum oxide that shows the Lewis acid site, but the result is opposite to the nickel tungsten. It shows the lower acidity because of the well-dispersed tungsten cover the acid site of the support. And for the nickel platinum, it not affect to the total acidity of the catalyst. For this figure shows the hydrogen TPR profile to see the reducibility of the catalyst, and it shows that for the nickel catalyst, it shows the reduction temperature about the 600 to 700. But after we add the molybdenum promoter, the reduction temperature decreased, and it means that the molybdenum can enhance the dispersity of the nickel oxide, and it also decreases the interaction between the nickel oxide and the support. And the result also opposite to the nickel tungsten, because the nickel, you can see the reduction temperature of this catalyst that shift toward the higher temperature. It means that the tungsten can increase the interaction between the metal and the support. For the nickel platinum, it shows the lower reduction temperature because of the effect of the hydrogen spillover, that the hydrogen adsorbed on the surface of the platinum can be transferred to the nickel oxide phase easily. To confirm the hydrogen TPR, we use X-ray absorption near-edge spectroscopy to find the amount of nickel active phase, and you can see that it shows the nickel oxide, the nickel molybdenum, nickel tungsten, and nickel platinum show the high amount of the nickel active phase. And to see the identification of the WTPO, you can observe that after we use the GCMS and the fractionation, the amount of the WTPO show the high amount of the naphthalene and its derivative. So in the next step, we use the naphthalene as the model compound for the hydrogenation to screen the catalyst. And this table shows that after we add the catalyst into the system, the nickel oxide, nickel tungsten, and nickel platinum can show the percent conversion of the naphthalene is about the 60%. But for in the presence of the sulfur, we use the thiophene added into the reaction mixture, and you can observe that the nickel platinum and the unpromoted nickel has not effective to hydrogenate the naphthalene, and it means that the nickel platinum and the nickel and the unpromoted nickel has a low resistance to the thiophene compound. And for the nickel, from the previous part, we use the nickel tungsten and nickel molybdenum as the catalyst for the WTPO hydrogenation. And you can observe that the color of the WTPO changed from the black color to the yellow color. It means that the unsaturated structure is removed to get the higher saturated structure. And this slide shows the hydrogenation of the WTPO. In this graph is for the nickel molybdenum, and another graph is for the nickel tungsten. And you can observe that it has like a competition between the sulfur compounds and the pH. And it seems that the sulfur compound like to absorb on the surface of the nickel molybdenum. It might be due to the higher acidity of the nickel molybdenum that can accelerate the hydrodesulfurization process. But for the nickel tungsten that has the lower acidity, it still has the available active site to absorb the pH and increase the rate of the hydrogenation. Anyway, the nickel molybdenum and the nickel tungsten need to use the severe condition to increase the hydrogenation rate and the hydrodesulfurization. In the conclusion, the addition of the promoter could decrease the nickel oxide crystalline size and resulting in the higher catalytic activity for the hydrogenation. And the platinum provides the highest naphthalene hydrogenation efficiency, but for the presence of the thiophene, the nickel platinum is not good. And nickel tungsten requires the long reaction time because it shows the higher reduction temperature, resulting in the higher metal support interaction. And the unpromoted nickel and the nickel platinum also show the low sulfur tolerance. Nickel platinum catalyst show the higher hydrodesulfurization, while the nickel tungsten catalyst prefer to the PAH hydrogenation. Thank you for the Asahi Glass Foundation, Britomat, and Department of Chemical Technology, Faculty of Science,ฬาลงกรณ์ University to support this project. Thank you very much for your kind attention.
Thank you, Professor Napida. This is a very good result for improve the waste time pyrolysis oil. So we have just a short time for question. Are there any question from the floor? Okay, if not, we have give a big hand to Professor Napida again. Thank you very much.
And the second speaker for this session going to be Associate Professor Dr. Sirilak Phumpadap from Department of Chemical Technology, Faculty of Science. She will be presenting on the topic of development of natural rubber composite for carbon dioxide absorption material. So please welcome Ajahn Sirilak, please.
Hello. Good evening, everybody. Thank you for this opportunity to talk with you today. And thank you, Mr. Chairman, for your introduction. Let me start off my work. As you know, the global warming resulted from the emission of the greenhouse gases has received wide attention. According to the greenhouse gases, carbon dioxide contribute to much more than 60% to contribute the high emission amount of the greenhouse gases that it comes from the combustion of fossil fuel, deforestation, and chemical processing. The carbon capture and storage technology is required to reduce carbon dioxide concentration in the atmosphere. Therefore, in this study, we would like to use the polymer material to be used as the absorbent to absorb the carbon dioxide instead of the activated carbon, zeolite, and silica. The synthetic polymer have been great interest because it showed the significant potential and commercial application. However, we have to concern the chemical toxicity and environmental safety. In order to make the eco-friendly environment, the natural rubber is an alternative material to develop for the carbon dioxide capture because it can be designed as the natural rubber foam with high porosity. The advantage of natural rubber are including the renewable material, eco-friendly material, friction resistant, flexible, good absorption properties, and easy to shape. However, the disadvantage of natural rubber are high temperature degradation and low selectivity for carbon dioxide. In order to improve the carbon dioxide absorption capacity of the natural rubber, in this study, we would like to modify natural rubber by using a diallylamine. And then the modified natural rubber was mixed with the modified silica particle to improve the carbon dioxide selectivities. Therefore, the objective of this study are, the first one is to prepare modified natural rubber foam composite filled with the modified silica particles. And the second one is to study carbon dioxide absorption capacity, the effect of temperature on the carbon dioxide absorption, and kinetic absorption of modified natural rubber foam composite. Here I would like to show you the method for modification of the natural rubber latex by using the diallylamine. After modification, we could observe the NH group too selective for the carbon dioxide. And then we would like to prepare the modified silica particle via sol-gel reaction. In this study, two effects of substituted size of silanol group and the amine content in the silane capping agent are investigated. On the left side, you can see that two groups of ethyl group and methyl group will vary for the substituted size of the silanol group. And on the right side, three kinds of the amine group are investigated. The first one is monoamine, diamine, and triamine. The formulation of the rubber compounding are shown in this slide. All ingredients were mixed by using a two-roll mill, and then the rubber compounding was subjected to the compression molding at 100 degrees Celsius for 9 minutes, and then is subjected to the oven at 140 degrees Celsius for 9 minutes. Finally, we could obtain the natural rubber or modified natural rubber foam composite. Here I would like to show you the FTIR spectra of the diallylamine, natural rubber, and modified natural rubber. After modification, we could observe the NH stretching vibration of the amine group at the wavelength of 3300 and NH bending of the amine group at the wavelength of 1642 and 1544. After modification, we could obtain that the carbon content, hydrogen content, and nitrogen content of the modified silica particle trend to be increased. The increase of the substituted size of the serenol group and the amine of the modifier affected the decrease of the surface properties. The modifier with less substituted size could be block the pore of the modified silica particles. Here I would like to show you the morphology of the modified silica particle using the scanning electron microscopy. You can see that the silica particle before modification show the spherical shape with the particle size in the range of 200 until 250 nanometers. And after modification, the modified silica particles tend to be aggregated or accumulated due to the increased basicity of its modifier. It is because the modifier can be acting as the catalyst to increase the rate of sol-gel reaction. Here, the same image of the natural rubber before and after modification are shown in this figure. Both natural rubber and modified natural rubber show a closed cell structure with an oval shape. However, the cell size of the modified natural rubber foam is smaller than that of the natural rubber foam. And the carbon dioxide absorption capacity of modified natural rubber is higher than that of the natural rubber foam. It is because the presence of the amine group increases the carbon dioxide selectivities of the material. And here I would like to show you about the effect of unmodified silica particles on the carbon dioxide absorption capacity. The carbon dioxide absorption capacity of the modified natural rubber foam increase after filling with the silica content. And the carbon dioxide absorption capacity of the modified natural rubber increase with increasing the silica content. And it reaches to the maximum by using the silica content up to 15 pHr. After filling with the silica content more than 15 pHr, the carbon dioxide absorption capacity tends to be decreased because the poor dispersion of silica particles in the rubbery matrix. Accordingly, the optimum content of the modified silica particle in this study was chosen at 15 pHr for further preparation of the modified natural rubber foam composite. Here, the effect of the substituted size of the modified silica particles on the carbon dioxide absorption capacity is also discussed. The modified natural rubber with the ethyl siloxane group show the higher carbon dioxide absorption capacity compared with the modified natural rubber mixed with the ethoxysilane group. It is because the steric effect of the ethyl group structure in the silane coupling prevent the active site for the carbon dioxide capture. And the effect of the amine content on the modified silica particles on the absorption capacity also investigated. These results show that by increasing the amine content, the carbon dioxide absorption capacity of the composite material tend to be increased. It is because high carbon dioxide selectivities was achieved by the amine group on the modified silica particle surface. And this slide shows the carbon dioxide absorption capacity of the modified natural rubber foam composite at different temperature. You can see that the carbon dioxide absorption capacity tend to be increased with the increase of the temperature. It is because the structure of the modified natural rubber foam composite and the modified silica particles become more flexible at high temperature. Therefore, the active site for the carbon dioxide capture was not hidden. However, the carbon dioxide absorption capacity of the modified natural rubber foam decreases when the temperature is increased more than 60 degrees Celsius because the structure of modified natural rubber foam may shrink compared to the modified natural rubber composite. Also, the kinetic data for the carbon dioxide absorptions on the modified natural rubber foam composite will be shown in this slide. Three kinds of the model is studied including pseudo first order, pseudo second order, and alarming model. The results show that the carbon dioxide absorption process for our sample was fit well with the alarming model according to the R-square was list 1. This result can be explained that the absorption mechanism for the modified natural rubber composite material was the combination of the physisorption and chemisorption. According to this result, we can conclude that modified natural rubber was successfully prepared by modified natural rubber with diallylamine. The carbon dioxide absorption capacity of the modified natural rubber increased compared to the natural rubber. The increase of amine content enhanced the carbon dioxide absorption capacity of the modified natural rubber foam composite. And the kinetic study of the modified natural rubber foam composite was fit by using an alarming model. Accordingly, this modified natural rubber foam composite can be a candidate for using as the absorbent material to decrease the carbon dioxide greenhouse gases in the atmosphere. Finally, I would like to thank the Asahi Glass Foundation andฬาลงกรณ University for financial support. Thank you for your attention.
Thank you very much. So we still have time for a few questions. Is there any question from the floor, from the audience? Please.
From Untitled and GC subsidiary. Can you give us some examples for the use of this rubber composites in industry or daily life?
Okay. Thank you for your question. Now, in the commercial, there is no use the rubber material. But in my idea, I would like to use this material to decrease the carbon dioxide release from the car or the transportation. For example, we can put the rubber sheet at the parking area or the gas station. And then now we have to concern about after absorption, how to dissolve to increase the value of carbon dioxide that released from our material. Thank you.
I have a question about the amine group that you modify on the rubber. You use the ring, secondary amine with the ring structure, right?
No, in this study, no.
On the rubber, the amine.
Yes, after modified by using diallylamine, this structure can change to the ring.
Yeah. And
Cyclization reaction occur.
Yeah, but compared to the one that you modify on silica particles, it's different amine group.
The high efficiency for the carbon dioxide absorption capacity is better for the tertiary amine in the linear structure, not in the cyclic structure.
I see. Okay. Okay, so is there any more question? So if no more question, please thanks Dr. Sirirak again.
Okay, the next speaker is Associate Professor Dr. พรณภา สุจริตวรกุล from Department of Material Science, Faculty of Science. She will present about the efficiency and photo stability of some photocatalysts for environmental purification and clean energy production. So please welcome Professor Dr. พรณภา สุจริตวรกุล.
นี้ใช่ไหมคะเป็น PDF เนอะไม่ใช่สไลด์เอาเป็น PowerPoint ซีรีส์ละเปิด PowerPoint ไม่ได้อะค่ะ
แต่เมื่อกี้เหมือนเขาเอาลงแล้ว มีแต่ PDF
ใช่ค่ะ
แต่เมื่อกี้เขาเอาลง
เป็น PDF นะไฟล์อาจารย์ไม่มีอะค่ะเป็น PDF แทนแล้วกันนะคะ
พี่ที่เวลามันเลื่อนมันไม่ได้กดจะไม่ใช่ไหมคะ
เป็น
มันเลื่อนสไลด์
ห้องนี้ก็ดีนะห้องเล็กแบบไม่ค่อยดีมากห้องใหญ่มันดู
ต้องใช้เลื่อนเอาอะค่ะ
มีความตื่นเต้นเลย
หาไม่เจอค่ะ
Thank you, Chairperson, for introduction, and good morning, everyone. So today I would like to present my research work and some parts of my result related on the topic of visible light-driven metal rope sodium tantalate photocatalyst, and why we interesting in this topic area since the crisis of energy and environmental pollution. There are two main major problems on the world today. And recently, as a researcher, to searching and developing new materials with clean and can be used with renewable energy as solar light and green technology is of our interest. Since our group focus and working on photocatalyst materials. Why? Because of photocatalyst materials is well known as one of promising materials that can be just activated by light, and it can produce high oxidizing power superoxide and hydroxyl radical that can decompose harmful organic substance, and also the byproduct is carbon dioxide and water that are like eco-friendly byproduct. And also in this process, there is no fuel requirement, no any energy supply, and also no chemical precursor. That's why the photocatalyst materials have been widely used in various applications, such as antibacterial, and also the most widely used nowadays is for air and water purification. And also, if you can heard about the self-cleaning surface, many material now develop self-cleaning surface by using photocatalyst materials. And recently, the topic about the energy production, like clean energy, this is hydrogen production from the overall water splitting by using the photocatalysis process, is very famous topic nowadays. Since the photocatalytic activity have high efficiency, the process is quite simple and low cost. This all process we can call is like an environmental friendly process. For the photocatalyst material using for hydrogen production, the important factor that there is the band structure of the semiconductor. The band structure of semiconductor could choose cover the oxidation and reduction potential of water to produce oxygen and hydrogen at valence band and conduction band. So it means the conduction band level of the semiconductor should be more negative than hydrogen production level. And for the valence band, it should be more positive than water oxidation level, as shown in this. And this diagram shows various kinds of semiconductor that each semiconductor that have the characteristic of the band potential. And for the purple line, all this material have the potential as a photocatalyst for overall water splitting. Since you can see the conduction band and valence band is covered potential for potential oxygen and hydrogen. So many kinds of photocatalysts, like if we know about many metal oxide, such as titanium dioxide, but in this work, we focus on the perovskite type photocatalyst. Since this type of semiconductor have excellent photocatalytic activity, and they have a good electronic property, and also the band gap of this material can be easily modified by doping with some metal ion or some ion to make it can be activated under visible light. Among various of perovskite structure, so sodium tantalate is one of the material that was reported. This material have superior property over other semiconductor in the case of they have high positive potential for hydrogen production, and also they have very high stability after photoreaction, and also it have high stability for light corrosion. It can be used as long time, but for only band structure, more than the band structure, we also have to consider about the size and morphology and also crystallinity of the semiconductor. This parameter it can be controlled by the synthesis process. So in this work, we select to use hydrothermal process, which is the low temperature, and we can control size, morphology, and shape of the particle at low temperature compared to other solid-state synthesis. Anyhow, the limitation of this material, that because it have wide band gap energy about 4 electron volt, this material can be activated under only UV light. So the challenge is how to improve this material can be activated under visible light, because of the energy, the spectrum of sunlight or solar energy come on the earth. It contains mostly more than 44% as visible light. UV light is very small amount, less than 5%. So if we can improve this material can be activated under visible light, it will be effectively utilize sunlight or renewable energy. Then it comes to the objective of this work. We would like to prepare the visible light responsive sodium tantalate by doping with chromium ion and using hydrothermal process. And then we evaluate the photocatalytic efficiency by degradation of organic dye and also the hydrogen production via water splitting. Let me show this simple synthesis process. We just starting with the tantalum oxide, sodium hydroxide mixture, and then we get the suspension and transfer in autoclave at 180 for 24 hours, and then we separate the powder, we wash and dry, then we get the sodium tantalate sample and make it characterization. For the doping material, we use the dopant as chromium oxide and vary amount of chromium dopant 0 to 88% by mixing in the beginning of the suspension. This is a XRD of doped and undoped sodium tantalate. We can see that all is well crystallized sodium tantalate in orthorhombic structure, and there is quite pure, no any other phase. But at more than 6% of chromium doping, we can observe small amount of chromium oxide peak. It means the excess amount of chromium doping becomes precipitate as chromium oxide. And when we enlarge the peak at 22.9 degree, we can see the systematic shift of peak to larger wavelength. It means that the lattice, unit lattice is become shrink or become smaller because of the substitute of chromium ion which have smaller size than tantalum ion. This one of result confirm the some substitution of chromium ion. The SEM observations show morphology of sodium tantalate. Pure sodium tantalate is cubic-like morphology, but when in the right hand, when we dope the higher amount, we can see the mixed morphology of sodium tantalate and chromium oxide. Is confirmed the XRD result, and the EDS elemental analysis confirmed the existence of only tantalum, sodium, and chromium in the sample. BT surface area show that when we dope with chromium ion, the surface area slightly increased. But when higher amount of chromium ion was doped, the surface area had decreased because of the precipitation of large particles of chromium oxide. So we would like to know the chromium ion species exist in our sample. So our sample we measure by the X-ray absorption near age structure by compare with standard chromium oxide foil. So we can see that all sample have the peak match and fit with chromium oxide foil. It means that all chromium ion in sample species of chromium ion is in chromium 3+. For photoluminescence spectra measurement, we can see that the pure sodium tantalate and after dope with various amount of chromium, the spectra intensity become decreased when we dope with chromium. It means that this doping with chromium can decrease the charge separation of, inhibit the recombination of charge carrier of that produced by the process. It means that this one will help for the enhanced for photocatalytic activity. We select the dope and undoped sample to measure the visible UV visible absorption spectra, and we can see clearly that for pure sodium tantalate, the absorption age is about 300. When we dope with chromium, the absorption age slightly shift to longer wavelength, and there is some characteristic that from chromium and tantalum have some charge have some electronic charge transfer, and also we can see the band gap energy when we dope with chromium 2%. The band gap energy slightly decreased from 3 to 3.8. But anyhow, this band gap energy is still wide for using under visible light. We test for the photocatalytic activity degradation of methylene butyrate, and it can see from this result, the sample doped with chromium have higher activity for degradation of organic dye compared to pure sodium tantalate under visible light. And also we pick the base sample to test under degradation of rhodamine B, because rhodamine B is stronger for decomposition than methylene blue, and we also can see the result that the dope sample can show the higher activity compared to the pure sodium tantalate without doping under visible light. But when we test for the hydrogen production, we not succeed to get any hydrogen production from this material. That we turn to consider about the morphology, improve the size and morphology of the material by changing the synthesis. We call two-step synthesis by adding one step before hydrothermal by treating the starting materials one step. Just mix the powder and keep in oven. Heat treatment we think the heat treatment can convert tantalum to soluble tantalate precursor and help to the crystallization after in the hydrothermal. And also we use glycerol as a size controlling agent and to inhibit the particle growth of during nucleation. And other process is same as previous. So this you can see the morphology of sodium tantalate produced from second two-step synthesis. The morphology of the particle becomes spherical compared to the previous one step is like a cubic shape. And the ratio of glycerol and water and time have effect on the morphology and the dispersivity and also the homogeneity of the particle. So we shoot this sample to further investigation by comparing the result of one step and two step. We can see that the XRD pattern show all the same and real crystallinity, but when we calculate the crystalline size by Schreier equation, the slightly decrease of the particle size was obtained when we use second step synthesis. For the adsorbent spectrum, it also compare between one and two step. The two-step synthesis with smaller particle can shift the absorption age to less shift, or it means longer wavelength. It can be respond more in longer wavelength. And then the sample was tested for the rhodamine B degradation, but this one, because of undoped material, we test under UV irradiation, and we found that the best condition for degradation it comes from the sample by using 1:2 ratio of glycerol and water and hydrothermal at 6 hours. So this means the time for synthesis is also very important to get the morphology and size, and also enhance to effect on the photocatalytic activity. Finally, we measure the hydrogen production of this sample, and we found that we can get the hydrogen production, but the amount is still very small. Anyhow, when we compare with the previous research, previous reference that we follow this paper, we use lower temperature, but we can get the more higher activity of hydrogen production, and we calculate the band structure of conduction and valence band of this material is cover the potential for hydrogen production from water. So in the conclusion, we can synthesize visible light responsive photocatalyst by pure or by and doping with chromium ion, and this material can degradation of dye and also can produce hydrogen production. Anyhow, to improve the activity under visible light of chromium doped sodium tantalate is still going on research, and we try to still develop this material. So finally, we'd like to thank Asahi Glass Foundation, Pitomat, and Synchrotron and Nagaoka University for financial support and also for characterization support for this research. Thank you for your attention.
Okay, thank you, Associate Professor Dr. Pornapa. Then we will move to the next speaker.
Yes. So the fourth speaker today going to be Professor Dr. Somkiat Tangchit Sikjareun from Department of Industrial Engineering, Faculty of Engineering, on the topic of intelligent monitoring and estimation of surface roughness and straightness in the CNC turning. So please join me in welcoming Professor Dr. Somkiat.
Good morning, ladies and gentlemen, and all อาจารย์ Oyo gozaimasu. Yes, I'm Somkiat from Department of Industrial Engineering. Yes, so today I'd like to introduce my research work on the intelligent machine. So the title of my talk is like intelligent monitoring and estimation of surface roughness and straightness in the CNC turning. So the contents of my talk today just like introduction and how we monitor the surface roughness and the straightness in the process during the turning, and also we apply the neural network to help to calculate surface roughness and the straightness during the process. And of course, we go to the next experimental setup and the cutting condition, and then to see the result and discussion. Finally, go to the conclusion. Yes, in fact, as we know that the CNC turning machine is quite important machine. However, in the future, we try to develop this kind of machine to be the intelligent. As you know, AI is coming, so that's why the intelligent machine is held at, yes, and serve, yeah. In the future, we try to develop like a humanless operation, so that's why the in-process monitoring is quite important. And of course, the surface roughness and the straightness is the critical dimension for the mechanical part, yeah, before bring it to the assembly process. So that's why this research, yes, happen. So again, and the cutting condition is mostly very important in the cutting condition, just like a cutting speed, feed rate, depth of cut, and tunnel radius, and also the leg angle. So this kind of cutting parameter will be considered in the monitoring system, yes. And come to see the idea, yes, what the idea of the research that, of course, during the cutting, we can see the dynamic cutting force, so we can obtain it from the dynamometer, just like a force sensor. We equipped it in the tune turret of the CNC machine. Yes, as you can see that we can see the cutting force. Yes, show you like a three-dimensional components. Yeah, we have the main force, feed force, and radial force. And again, during the cutting, we just consider and we think that during the cutting, we can see the feed mark, and the feed mark can, help you to monitor the roughness, even the straightness. In fact, the roughness profile and the straightness profiles are the same, but the difference is the roughness you calculate it from the area, but for the straightness you calculate it like flatness or like the line that yeah, something like not leveling line. Yes, okay. So from this idea, so we think that if we can prove that the cutting force or the dynamic cutting force is had the profile same with the roughness and the straightness, so we can use the dynamic cutting force to estimate the roughness and the straightness during the process. That means in process, so we can avoid the reject or rework, so we can achieve the 1 part per million. That we can reduce the reject, something like that. So, and the purpose that we try to use the ratio of the feed force to the main force in order to eliminate the combination of the cutting condition and the hardness of the material. And again, we also use the dynamic force from maximum feed force to the minimum feed force divided by the static feed force to eliminate the hardness of the material to estimate the straightness. Yes. According to this, and how can we prove that the dynamic cutting force correspond to the surface roughness and the straightness profile? We utilize the FFT or fast Fourier transform to see it in the frequency domain. So now we have to check the peak of the roughness and the straightness that should be corresponding with the peak of the dynamic cutting force. If it happen the same frequency in the frequency domain, so we can conclude or it's implied that we can use the dynamic cutting force to predict the surface roughness and the straightness. And again, once after we prove this, so and how can we calculate it? Of course, we use the neural network like Lowenberg and the backpropagation technique to help to calculate during the process. And you can see that we have the 7 input like cutting speed, feed, depth of cut, no radius, rake angle, and of course the static force ratio and the dynamic force ratio to the static force ratio here. Yes. Then, as we know that we have the MATLAB, yes, program from the university at the real license, so that's why we adopt that and help to calculate it. Yes. So we just use the neural network function from the MATLAB and training and validate it. And after that, we just bring the algorithm to predict and estimate the roughness and the straightness in the process. So, and this is the cutting experimental setup. As you can see that we equip the dynamometer on the tool turret. Yes, and also have like a cutting tool that coated carbide and also use the AL6063 aluminum. Yes. Yeah. And this the major cutting correction that we apply and we train the system. Yes, we use the aluminum 63 and cutting speed 150, 200, and 250 meter per minute. The feed rate 0.1 up to 0.15. Yes, depth of cut 0.1, 0.2, and 0.3. And different two node radius 0.4 and 0.8, and also the different leg angle negative -6 and positive 11. So we come to see the preliminary experimental result. Yes, that I try to show you that you can see that the upper left hand side show you the dynamic cutting force that we obtain from the process during the process, and the right hand side just the frequency domain of themselves, in the main force, feed force, and thrust force, yes. And below show you the roughness on the left-hand side and the power spectrum of itself at the frequency domain. So you can see that the surface roughness, both in the cutting force and roughness profile, it show you at the same frequency. So it implies that, so we can now use the dynamic cutting force to predict the roughness during the process. And again, this also show you the straightness. the same technique we use the fast Fourier transform to prove the spike or the peak of the straightness at the frequency domain, both dynamic cutting force and the straightness. So it appears the same frequency at 17 Hertz. And again, we come to see the cutting parameter that has the impact or has the significant something like this. So you can see that when we change the cutting speed, so the straightness reduce, yes, and also even the feed rate, when you increase the feed rate, the straightness also increase. This had the reason that the feed rate just like theoretical surface roughness and straightness, that when you increase the feed rate, the roughness and the straightness increase, and the cutting speed help to reduce, yes, the roughness and the straightness when you increase, because the material becomes softer and can easy to cut, so that's why. And the depth of cut, when you increase the depth of cut, the cutting force increase and tend to obtain the higher roughness and the higher straightness, so that's not good. So, and the two node radius, when you increase it, you can see that the straightness and the roughness reduce. According to this, the node radius can help to reduce the feed mark. That's imply that can reduce the feed mark or roughness. So, and this to show you that when we train it and we test it before we bring the algorithm or the function to predict during the in process. So this has the high correlation over or exceeds 95%. So that's why we develop the algorithm. The next one, in order to put it in the controller of the machine. So whenever or whatever you input the cutting correction in the machine can adjust and can adapt itself to avoid, yes, or to reduce the roughness and straightness, yeah. And then if the cutting tool is worn or is reached the life, so we have to repair the new one. So, and this algorithm have been proved again with the new cutting correction here, and this time we also use the cutting correction that's out of the range that we train it. When we train it from the 150, but now we started from 180 and use the 260 and try to check that this algorithm that we say that the cutting force ratio can help to eliminate or can cut off the effect of the cutting condition or even the hardness. It's just like a dimensionless. We are going to do the dimensionless, and the machine can be intelligent and humanless, even though the cutting correction change. Yes, by using the neural network. So again, so this to show you the result from the new cutting correction. The above graph show you the roughness, that RC and RA, the maximum to peak and the average roughness. So you can see that the measured one and the predicted one are close together. Even the straightness from the lower one, so you can see that the predicted and the measured, yes, close together, but somehow you can see it's a bit far because of this cutting correction is out of the range that you trained it before. But anyway, this kind of predicted value we can exhibit because it's close to the measured one within plus and minus 10% error. Yeah, so according to this, I like to give you the conclusion that the in process, yes, prediction of the roughness and the straightness, yeah, are proposed and developed utilizing the neural network, yes, and use the cutting force ratio to predict, yeah, and the relation between roughness and straightness has been examined, investigated, yeah, with the cutting speed, feed rate, depth of cut, to no radius, and also the rake angle. So, and the in process roughness and the straightness, yes, can be predicted and obtained with a higher accuracy with the two-layer feed-forward neural network with the sigmoid hidden and the linear output neural. Yes, yes. Yeah, this work had been performed and supported by the Asahi Glass Foundation, Japan, 2019. I would like to, yes, thank you very much. Yes, for the financial support and for your kind attention. Thank you very much. 本当にありがとうございます。Any question, please?
Is there any question from the floor? Or? Okay, so if no more question, let's thank the speaker again for his sharing the research. Thank you very much.
And the last speaker, we will go to Assistant Professor Dr. Sojipong Chatraporn from Department of Physics, Faculty of Science. He will present about the investigation of defect states from radioactive emission in a complex system by photoluminescence technique. Okay, please welcome Dr. Sojipong, please.
Thank you, Mr. Chairman, and good morning, everyone. Today's my talk is about investigating the defect states in semiconductor material known as CIGS that's used for solar cell application. I will start my talk with the motivation of the research, and then I'll give you a brief introduction about CIGS materials and the fabrication process. And then I will talk about band gap engineering in these materials and the tools that we use to investigate defect state in this material, especially the optical and photoluminescence spectroscopy. And in this method, we can obtain the energy gap and can probe the defect state or defect levels. And in the end, I'll summarize our research. Okay, the motivation of our research is about improving the efficiency of solar cells, and CIGS is one material that has been known for about 4 decades. And today, best efficiency for the lab scale device is about 23 or reaching 24%, comparing to a new material, perovskite, that has received a lot of attention these days. So CIGS is a ternary compound, semiconductor compound that consists of group 1, that is copper, and group 3, and group 6. Okay, group 3 can be alloy between indium and gallium, so that the energy gap of this material can be tuned between 1 and 1.7 electron volt. Okay, the advantage of this material is that it has a very high absorption coefficient in the order of 10 to the 5th per centimeter. That means we can use this material in a very thin layer, like 1 or 2 micron, can absorb all the sunlight that shining to this device. Okay, the device fabrication, it has a multi-layer structure. The substrate is normal glass that you can see everywhere, like that you use for windows. This is known as soda alarm glass. And molybdenum is used as a back contact. It's a metal. And CIGS is a photon absorber. The thickness is about 2 micron. That's very thin. Your hair is about 60 or 50 microns. So the thin layer of this material can absorb all the photons. And the upper layer are the N-type semiconductor. I forgot to mention that CIGS is P-type semiconductor. And zinc oxide is used as a window layer so that the sunlight can come through. Aluminum is used as the front electrode. This is what the lab scale device look like on 3 by 3 centimeters square. Okay, that's the structure. For the material study, we will not complete the whole structure. We will fabricate up to this layer, CIGS on molybdenum on soda alarm glass. The normal structure, the band diagram, I will not go into the detail much. The 112 CIGS, that is the, I forgot to mention, 112 CIGS has this molecular formula like this, 1 copper, 1 of group 3, and 2 of group 6, 135, 1 of copper, and 3 of group 3, and 5 of selenium. And we have the normal structure of 112 looks like this. The band gap of this 112 CIGS is about 1.2 that we fabricate in the lab. And what's found that the 135 CIGS was accidentally found on the surface of 112. And now in our research, we try to intentionally put a very thin layer of 135 on 112. And 135 was found to be N-type semiconductor instead of a P-type as the 112. And people propose that the 135 will affect the band diagram in the valence band instead of a conduction band. So the advantage is it will propel or push away the hole from the junction and increase the band gap. When the band gap increases, the voltage or the open circuit voltage will increase as well. So we try to intentionally put different thickness of 135 on 112. And we found that this is the photovoltaic performance. This graph on the left, upper left here is the value of the open circuit voltage. The standard device has the VOC average about 640 millivolt. But when we put 135 for the thickness of 5, 10, 20, or 40 nanometer on top of 112, we can see a significantly increase in the open circuit voltage. However, the current of this device with the 135 capping layer decreased a little bit. When we look at the efficiency of the device that we have 135 on top of 112, it's comparable of 112. However, the open circuit voltage was significantly increased. And then we want to see what the 135 actually did to the 112. First thing that we probe is that did it actually increase the energy gap? So we measure the transmission and reflection. This is transmission curve, and below here is a reflection curve from 1400 nanometers down to 700 nanometers. And we can turn this data to find the energy gap. Okay. The energy gap of 112 in black here is about 1.15. But when we put 135 on top of the 112, we can see the chip to the higher energy. This is only 135 here. 135 has the EG very large of 1.45 compared to 115 or 112. So when we have a very thin layer of 135, you can see a chip to higher values of energy gap. So the 135 actually did something to 112, according to our data here. And the energy gap doesn't tell you about the defect state. By using the transmission of reflection measurement, an optical probe or an optical technique that people can use to investigate the defect state is called photoluminescence. The idea is we have some very intense light source, which is a laser in this case, shining to a sample, a thin film of CIGS, and see what happened. Okay, when it's shined with some laser, it will produce some electron hole pair and then emit some energy that's called a luminescence. And it can be detected by a spectrometer or monochromator, and we can use that data to interpret what happened in the material. This is what it looks like. We have laser coming from a source. the sample is here in the cryostat that we can control the temperature from room temperature down to 10 Kelvin. And then the luminescence is emitted in front of the cryostat and collected by the lens to the detector. And I would like to mention about all the radiative recombination paths that possible when we do the PL measurement. The first one is interband transition. This will give you the EG. The next one is called the free to bound. This is all the free to bound as well. The black dot, electron, white dot representing hole. And here that we have the state lying in the band gap. This is called the donor to acceptor. And we are going to concentrate in this transition or recombination path. First thing, after we perform the PL measurement of 135 with a power dependent, meaning we can adjust the power of laser. So the black curve is highest intensity down to 20% of the maximum intensity. For the 135, we don't see any difference except a small chip. We saw a broad peak for the luminescence in 135, but in 112, when we reduce the power of laser, when we have a highest power, we saw one sharp peak, but the laser power, when it decreased, peak splitted, and those are assigned to free to bound and donor to acceptor pair or DAP. Similarly, for the 112 that we have a thin layer of 135 on top of it, the nature is quite similar to 112, but we don't see any emission from 135, so we don't see the next signature of 135 on this bi-layer system. Okay, and now when we do the temperature dependence, for example, we measure the PL from 10 Kelvin up to room temperature of 112. You can see the peak shifted to shorter wavelength. This is called a blue shift, which is the nature of P-type semiconductor, as well as the sample that we have, 10 nanometer of 135 on top of 112. We saw the blue shift, the horizontal axis is wavelength. For the 135 only, we saw the red chip in state. So this is the nature of N-type. This is the nature of P-type semiconductor. And when we consider the peak energy of these materials, the 112 and 112 with a capping layer with 135 show the increase in the peak energy when we increase the temperature. On the other hand, for 135, the peak energy decreases when we increase the temperature. And to find the activation energy, we need to use the two-channel Arrhenius equation from our PL measurement to fit for this EA1 and EA2. I0 is the intensity at 0 Kelvin, and IT is the intensity of the PL that we measure at temperature T. So A and B are the fitting parameter. By doing all the fitting, we can come to the energy diagram of 112 that the activation energy of 10 to 30 milli-electron volt is below the conduction band, is designated for selenium vacancy, and 50 to 90 MeV above the valence band. That is the state for defect state for copper vacancy in this 112 material. And 135, thin layer of 135 and 112 is not much different, but the 135 only, we have 1 through 3, 4 emission energy that contributed by the deep level defect that is known as group 3 substitute in the copper site. So this is a case of only 135, and we do not observe this transition when we put some 135 on 112. And this is the temperature dependence of a various thickness of 135 on 112. It started to be a blue chip for a very thin layer and shift back to red chip when we have a thicker layer of 135. So we can use the optical process to investigate the EG, and we found that the EG increases as 135 thickness increase or gets thicker, and PL can be used to probe the defect states in CIGS material. Donor to acceptor pair and a free to bound transition were observed in 112 and 135 on 112 bilayer. And only DAP, donor to acceptor pair transitions, can be observed in only 135. The defect levels, about 10 to 30 MeV below the CB, is designated for selenium vacancy in this material. And 50 to 90 MeV above the valence band is for the copper vacancy. And as I showed before, that substitution of group 3 at copper site only found in 135 material. And I would like to acknowledge the financial support from Asahi Glass Foundation and Thailand Center of Excellence in Physics, and also the Department of Geology for access to the XRD measurement that is not shown in this work. Thank you very much for your attention.
Okay, thank you very much, Assistant Professor Dr. Sochipong. And now we will have time for short question. If anybody have any question, if not, we will be the end of this session. Thank you very much.
Thank you.